So in this video, we're going to go over several identities and inequalities involving integrals, all of which I think are probably pretty obvious or at least pretty easy to prove if you replace the integration symbol by a summation symbol. So I'm going to do something a little unusual for my videos. I'm going to state a bunch of these formulas all at the beginning and then go over the proofs all at once towards the end. So the first formula, which is often called, the first two formulas I guess are really both called linearity formulas. And they say the following: if I have three numbers a less than b less than c, then the integral from a to c of f is equal to the integral from a to b of f plus the integral from b to c of f. And then there's this extra little clause that I did at the end. That's true when both of the integrals on the right-hand side exist. I think this formula itself is probably one that you've seen before in calculus. It's certainly something that you should probably be able to guess based on sort of our intuitive understanding of what an integral is. The integral from a to c of a function f is the entire area shaded here, and the two formulas on the right-hand side are the area under the blue crosshatch line plus the area under the green crosshatch line. So of course they better add up to the same thing. The one part that's a little bit new here compared to what you saw in calculus was that I'm assuming here that both of the integrals on the right-hand side exist. So that is, the theorem is really saying two different things. The first is when these integrals both exist, then the third integral, this one, also exists. And furthermore, we have this identity. So there are really two parts, one of which is an existence result, and the second of which lets us do calculations. The next result is very similar for constants a strictly less than b, and some other constant c, and two functions f and g. The integral of f plus the constant times g is equal to the integral of f plus the constant times the integral of g. Again, I have this sort of second part of the theorem, which says this is true when both of these integrals exist. So when these integrals exist, this integral exists too, and we have a formula for the value. Again, probably pretty familiar. The next inequality is one that perhaps you didn't even bother writing down in calculus class. If I have two integrable functions f and g with pointwise comparisons and f of x is less than or equal to g of x for all x, then I have the same inequality among the integrals. And again, I need both of these to exist for this to be true. Well, obviously, otherwise it's not clear what the formula would mean. This has two corollaries which are quite useful, the first of which is essentially the triangle inequality, but for integrals. And it says the absolute value of an integral is less than or equal to the integral of the absolute value when the left-hand side exists. So the only weird thing here is that the thing that I'm interested in checking here is that this one has to exist. Then this one also exists for free, and we get this inequality between the two integrals. So that part about existence is maybe not so obvious, and we're going to go over some examples in about 30 seconds to say why it's the left-hand side that needs to exist and not the right-hand side. And then finally, if I have an integrable function f, and I have bounds on f, that is little m is less than or equal to f for all x, and big M is bigger than f of x for all x, then I get a sort of obvious bound for the integrals as well. So again, there's sort of a picture that goes along with this. So I have my integrable function f over there. I have my big value, capital M, and the right-hand bound is just telling me that the area under the curve f is less than the area of this shaded region, and I have a very similar bound on the left-hand side. Okay, so that was a lot of theorems rattled off fairly quickly, and I'm doing that a little bit on purpose to try to emphasize the fact that you probably more or less know all of these bounds or all of these facts. Certainly 1 and 2, these linearity formulas are ones that you've used quite frequently in calculus class. The third one I hope is sort of clear, right? If I have an inequality between functions, of course the same thing is true when I integrate those functions. And then we have these two essentially immediate corollaries of this last fact. Okay. Before I get to the proofs, I want to say a little bit about why we need some discussion about when integrals exist for these theorems to be true. So I'm just going to give two examples, and these are really sort of the main counterexamples to the theorems that I just wrote. So first of all, I have this formula which says the integral of f plus g is equal to the integral of f plus the integral of g. When these two things exist, I do need that part of the theorem, that condition to be true for the theorem to be true. And there's sort of a silly example. If f of x is equal to 1 when x is irrational and 0 when x is not irrational, and I decide g of x is just minus f of x, well, obviously the integral of f doesn't exist, as we've already checked. The integral of g doesn't exist. Well, it's basically the same function. But of course, f plus g is 0, so the integral of f plus g exists. Okay, and is 0. All right, so that's sort of a silly reason that that the integral of a sum can exist even if the integral of the summands both don't exist. The next example about the absolute value is very similar. Here's an example where the integral of the absolute value of f exists, but the integral of f doesn't. I just define f to be equal to 1 for all values of x that are rational, and f of x is minus 1 for all x that's not rational. So that absolute value of f of x is just 1 for all values of x. So obviously, the integral of the absolute value on any finite interval exists, but the integral of f itself does not exist. Okay, so just a few simple examples. Obviously, I'm leaning on this one particular example for the indicator function of the rationals quite a lot, but this is basically what can go wrong with really all of these theorems when you have some of these integrals but not others existing. Okay, great. Having stated the theorem and given sort of the two main counterexamples that you should bear in mind when trying to use these sorts of theorems, we're now going to get into the proofs. I'm going to give careful proofs, and of course there are all of the details in the lecture notes, but this is one of those situations where I'd actually suggest that you give it a shot yourself. Just pause the video and try to prove one of the theorems. Might as well be the first one, it's one of the simpler ones, because there's really sort of one idea which is going to get you about 90% of the way there for all of these theorems. The first thing is that all of these proofs really have two steps. The first step is that we can replace integrals by finite sums with up to some error. That is, for every epsilon greater than 0, there exists some partition p, so that the integral from a to b of f is equal to this lower function, L of fp, plus some small number. I'm making up notation and calling that the error of fp, which we know is between 0 and epsilon. Another way of writing this in notation that's a little bit more familiar, but I think less useful, is that the difference between the integral and this lower function is less than epsilon in absolute value. Okay, so that's the first thing we can do, is we can replace integrals by finite sums and add in this tiny error term. And then the second part is that actually all of these formulas which I wrote down are essentially obvious for finite sums. So if you put these two things together, right, you can replace the integrals with finite sums, you can check that these equalities or inequalities are true for the finite sums, and then you have some tiny error epsilon, which is sort of arbitrarily small. Okay, so that's obviously a very sketchy argument, but I strongly suggest that you pause the video for a moment and just try it out for yourself. All right, I'll assume that you've done that, and I'm going to keep on going. For this video only, I'm going to define a little bit of shorthand for the next couple of arguments. I'm going to define error of fp, the error function, to be this upper bound function minus the lower bound function. It's just to stop me from writing u of fp and L of fp all the time. Great. So with all those preliminaries out of the way, let's start actually proving some theorems. So the first theorem, just to remind us, is I have three numbers a less than b less than c, and I have this linearity formula, the integral from a to c of f is equal to the integral from a to b plus the integral from b to c. So here's the argument. I'm going to go through the same two steps as I just sketched out. So I'm going to fix some epsilon greater than 0. Then there exists partitions p of ab and q of bc, so that the error term is small. These two error terms are both small. That's just really from the definition of the integral plus our integration condition. Okay, great. What does that mean? Well, the error of f on the union is just the error on the first part plus the error on the second part, and so that's less than epsilon. So that's our first bound. It's telling us that we can replace integrals by lower or upper functions and incur a total error of less than epsilon. Next, I have to say something about the lower and upper bound functions, but in this case, life is easy. The lower function, L of fp union q, is actually just L of fp plus L of fq, right? Talking about integrating from a to b to c, and of course, the area under this curve plus the area under that curve is equal to the entire area under this curve from a to c. Right? So that's a second fact, this double star that I needed. So combining those two facts, I get the following. integral from a to c of f is less than the upper bound function u of f comma puq. That's just what the upper bound function is, right? It's always an upper bound on the integral. By the linearity formula, that is double star, that's equal to u of fp plus u of fq. And then by my bound star, that's less than integral of f from a to b plus integral of f from b to c plus my two error terms, epsilon over 2. I get exactly the same bound for the lower bound functions, and if I put together this inequality and this inequality, I conclude that the integral from a to b of f plus the integral from b to c of f minus the integral from a to c of f is less than or equal to epsilon. Okay, which is exactly what I wanted. So that's it. Again, there's a fair amount of writing in this proof, but the sketch is quite short, and I think perhaps it's worthwhile trying to reconstruct it just once from memory to see that although there's a lot of writing, there's not a lot going on. The second argument is going to be fairly similar, but is slightly longer. So just to recall what's going on, I have three numbers a, b, and c, and two functions f and g. I have, again, this linearity formula, the integral of f plus cg is equal to the integral of f plus c times the integral of g, where all of the integrals are over the same region. I'm going to be doing this proof, and I'm going to try to mimic the argument that I just gave by writing in red all of the little bits that have to change. So I'm going to assume for now that c is strictly greater than 0. Otherwise, I may as well just replace g with minus g, and the proof is going to be essentially the same. And then the first part of the proof to get this star bound, this error function bound, is going to be exactly the same, except a few sort of cosmetic differences here. So again, I'm going to have a partitions p and q associated with these two integrals on the right-hand side of the equality that I want to prove. I assume that the error for each part is small, and that gives me a bound on the error for the union of the partitions. Okay. The second part of the proof does require a slight additional comment. So here's the second bound, double star. The lower bound function f sub l p union q plus c times the lower bound function g sub l p union q is less than the lower bound function associated with function f plus c times g. So this is very, very similar to what we did in the previous argument to get this bound double star. You'll notice in that previous argument, the sort of critical line was observing that the upper bound integral u of fp union q was actually equal to u of fp plus u of fq. Those two finite sum terms were actually equal. Whereas here, we have an inequality. And we checked this. This is an immediate corollary of some bounds that we had when we were first talking about infima and suprema way back near the beginning of the course. But it's easy to forget, so I just wanted to draw a picture to say that those inequalities really are necessary, they're not free. So here's my sort of little picture about why we need something along those lines. I'm going to give just an example. I have two functions, f and g, which I've drawn here. Okay, you may not be able to see that in the picture, but they're intended to be piecewise linear. And I'm assuming that my constant c is exactly equal to 1. So what's going on in this situation? Well, my function f plus my function g, when you add them up, you just get a constant line, which is this black curve here, which is f plus g. Now, if f plus g is constant, then obviously f plus g upper is also constant, right? For whatever part of the partition we happen to be picturing here. On the other hand, if you look at f upper plus g upper, something funny happens, right? So if you look at the points that get chosen, the largest value of f happens way back here at x naught at the beginning of the partition, and we get about a 0.5 according to the picture. On the other hand, the largest value of g happens right in the middle, and it has a value of 1. And so f upper is 0.5 and g upper is 1. And so f upper plus g upper is a constant function just like f plus g, but it's 1.5 rather than 1. Okay, so it's strictly larger. Okay, and because this is a simple example, it's much larger. What went wrong here? Well, when you're looking at the upper bound functions, you take the worst point for the function f plus g when you're looking at f plus g upper. When you're looking at f upper plus g upper, you take the worst point for f and the worst point for g, and if those two worst points happen to be different, you're going to get a bigger number in general. Okay, so that's what happens. Basically, we have an extra degree of freedom here compared to down here, and so we're going to generally get a larger number. Okay, that's why we have an inequality here, and it really is an inequality most of the time. If you're looking at the lower functions, you get the same thing. So I'm not going to bother doing the same picture. It's really the same thing. You can look at it minus f and minus g and find the same conclusion. All right, with that little aside out of the way, the rest of the argument is essentially the same as it was before, so I'm going to go over it fairly quickly. The integral of f plus constant times g is bounded from above by, well, these integrals associated with the upper bound functions. That's what we just did, double star. And then, of course, we can replace these integrals of the upper functions by the integrals themselves at some small error epsilon. So that's what we proved in star. Okay, so that gives you the upper bound on integral of f plus cg, and then you can get the lower bound on the integral from f plus cg, in essentially just the same way, but replacing all of the upper bound functions with lower bound functions. Okay. When you've gotten this all out of the way, you'll notice that you have an upper bound on f plus cg in terms of f plus c times integral of g, and a lower bound on the integral of f plus cg in terms of the integral of f plus c times integral of g. One typo there, sorry, that should be, of course, minus epsilon. Okay, and when you put those together, you get the conclusion you want. All right, finally, I'll talk about the third theorem. I have two functions, f, g from a, b to r, both of them integrable, and I have this pairwise comparison, f of x is less than or equal to g of x for all x, and the conclusion I want is the same inequality comparing the integrals. This argument is actually shorter than the last two, so it's sort of nice to end with something simple. Now we get the following. For every single partition P, we have the following. The integral, the upper bound of the integral u of fp is equal to the integral of the upper bound function fup. Okay, this is just what I mean by the upper bound function, so that equality is sort of by definition. I have a similar equality for g over here, and then I have the critical inequality, the integral of f upper is less than the integral of g upper. Why is that true? Well, that's true because remember, f of up and g of up are themselves piecewise constant functions with only finitely many pieces, which means that these things which I've written down as integrals are in fact finite sums with the same number of terms. So I have a pairwise comparison between the terms in the sum, and therefore I have also an inequality between the sums themselves. So again, the point is that this important inequality is sort of obvious for finite sums, and that's all that we're using here. All right, now everything just follows from the definition. The integral of f is the infimum of u of fp over all possible partitions, and since I have an inequality for every partition, that's less than the infimum of u of gp over partitions p, which is the integral of g. So that's it. All right, thanks very much.